So where are we? So we have constructed this category of motivic spaces. And then we had defined this stable normative category. You want number to be category, and there was a question last week which I was unable to answer, and so I want to say this now. So what I said is this lemma. So this was in the generality of a presentably symmetric monodal category, and I had some object which I was assuming is symmetric, and then we have I defined this C inverse, if you want. And what I said, and that was right, is the following. So this has the following universal property. So for any again symmetric presentably symmetric monodal category, I said that we have co-limit preserving monoidal functors out of this new category to this D, and so then I had I had this functor from C in there, which is kind of the natural length, and so then this I can compose, and I've co-limit preserving number functors from C to D. Okay, then we have to the evaluation of this object with C, it goes to D, and then here we had also the evaluation at C, and then I mentioned this Picard anima, which was the anima obtained from the full subcategory of D consisting of tensor invertible objects. Okay, and the question that Antoine raised, it was a good question, is why does it even land in there? So in other words, why is it true that if you have a natural transformation between two such functors, if you evaluate it on C, why do you automatically get an isomorphism? And this is true, and the lemma here is the following. So if you have some, let's say E, so this E would be this guy, and in there you have an object little e, which could be dualizable. Particularly, this would be implied by the tensor invertible. Yeah. This situation, and then you have the functor. You have two functors, let's say f and g to this d, and you have a natural transformation between them. So f and g are tensor functors. Then it is always true that if you evaluate this in a dualizable object, this is automatically an isomorphism. So this is a fact which I have put in the notes. This is even true for a dualizable object, in particular for a tensor invertible object. Yeah? And so in other words, if I have this f and g in here and I have a map between them, then this will be mapped to an isomorphism. So in other words, we do that in the anima, so in the sense that it's only going to hit isomorphisms. Okay. Yeah. So this is also something I think that I mentioned in this school lesson, and I had forgotten about this last week. So good. So this is a little bit of an addendum from last time, and now I want to go on with discussing the properties of this, and I will try to make this, not more and more abstract, but I'll try to state things in a way that don't necessarily use the specifics of this construction even. And one thing that we talked about last time was what about proper base change here? And I said this follows from projective base change, but I didn't yet say excuse me, something about projective base change. And so here is the statement that I want to make. So this is again like so many things here due to IU. So the statement is the following. So D, yes, it's frozen again. Okay, for me. Yeah. What's going on? This one maybe seems to be working. Okay, thank you. Yeah. So let me say this way here. So let's say D is a four-functor formalism. Yeah, is meant it's a symmetric monodal, Lex symmetric monodal functor from schemes op to PRL. Yeah, so in other words, we have F upper star, F lower star, intrinsic products and internal norms, but not yet the Schritt functors. So we have this, and this satisfies localization and a homotopy invariance, I would say A1 invariance, and then this tail object 1 twist 1 is, and I think I wanted to go just pre-RL stable just for safety. This is tensor invertible, which is the case for SH. And finally, B is a Zariski sheaf. Then, so all of these properties are satisfied for SH. Okay, so and then we can observe this. This D has base change with respect to projective maps. Yeah, and I think this is what I stated last time already, and what I have not explained much about is sort of the beginning of the argument. And I will say a little bit more, but not really say it in full. So this proposition, like I explained last time, comes from the following proposition, which is also to tell you that sort of from one special case, namely the special case under these assumptions, D has base change for these most basic maps, namely Pn S to S. Yeah, so this is that's what will apply this under these Schroeder conditions. And so, and this is somehow an annoyingly simple statement with an annoyingly hard proof, or hard, but let's say complicated proof. And so I thought a long time about it, and in the end, I decided not to really give you the proof, but I will still at least want to say sort of one part of the thing. So I remind you, so by this P, so what we want to show is E lower star commutes with, let's say, F upper star, and we have this projection formula, right? Which was the linearity of this P lower star, which otherwise might not generally be true. Yeah, so that's what we want to show, and we already know this for this lower for the lower sharp functors. And so the goal is to relate this lower star to the lower sharp. And in order to do this, one can proceed as follows. So the strategy is the following. So one constructs an isomorphism. So we will, let's say, construct an isomorphism between this, so this is my map P lower sharp, and P lower star. Well, not quite. Yeah. So remember, this is the left adjoint of upper star, and this is the right adjoint. So if you already know something about these functions, you will see this cannot quite match. So there must be a kind of a massage here to this term. And indeed, there is some such correction, which I denote by sigma P here. And so what I'm trying to do now is to explain to you what this sigma P is and wave a little bit in my hands why somehow this works. So what is this sigma? So this is the so-called tone space construction here. Here is its definition. So once again, you should think of this as being kind of, not should think of this. This is going to be a certain autoequivalence of this D on this base scheme S. Yeah? So this will be an equivalence under all these assumptions, notably this invertibility of the tape twist. And you, with a bit of a simplification, you can think of this sigma P roughly as you twist P times and shift 2 times. However, this is only true for so-called oriented commodity theory. So this is not always true, and that's also part of why this this proof is actually more complicated than you might want it to be. But anyway, let me at least try and say what this is a map from X to S. So this will be, for example, this P in a moment. And we have a section S. So let's say we have this, so where f is smooth and s and f is the identity, then there is this so-called tone space functor or tone functor, I don't know. So this depends on these two maps here. And so this is f lower sharp s lower star. So this goes from d of s to d of s. Okay, so that's some functor. Okay.
I suppose the P is an N.
Oh yeah, the P is of course an N, maybe that N. I think. Yeah. So this is a certain end functor. And how can you somehow think about it? Well, you want to observe the following. So if this is your f, then you have here the inclusion of x minus this thing. So this is the complement of that section. So let's say we call this G. Then we have a localization triangle, which is G lower sharp 1 maps to F lower sharp 1. And then this maps to this tone guy applied for 1, right? Because now we are using this localization sequence. We have the 1 here. Then the next one would be the S lower star 1. And then the complement would be the J. This is J lower sharp 1. Yeah. So we have such a fiber sequence. So in other words, you want to think of this as being quote unquote x modulo x minus this section. Yeah. So you kind of collapse the rest, everything else but the section to a point. That's the idea of this thing. This comes from topology here. This name, Tom space, and it's used there a lot. And it is, so now why is this relevant? So this is true. So now I can do this for any such smooth Weber section. We are applying this now as follows. So given now any smooth again f from x to s. So this f will be our p in a moment. We can define this again this tone space functor or tone functor to be this guy there applied to the second projection and the diagonal, right? So we have here the usual diagram, x times x, the delta, and the two projections, and so this is PR2. Then we have this section, yeah. So we can apply this. So once again, it would be delta lower star and then PR2 lower sharp. Okay, so that's the definition of this guy here. And then one can produce a natural map like this, which I also really want to say. So we have a natural map F sharp to this guy there. How does this go? So F sharp is F sharp composed with PR1 lower star, delta 1 lower star, right? So this is using that we have the identity here. And now I can use that this F lower sharp is the left adjoint F upper star. So I get F lower star PR2 lower sharp, yeah, using the base change in this square here. Yeah, so here this uses smooth base change. So I have such a natural map if you unwind it, yeah. And then I have delta lower star here again. And this was exactly the definition of this F lower star sigma F. Okay, so there is a certain natural map between this left adjoint and a kind of a tweaked version of the right adjoint. So this is easy to somehow define and to write down, and then the hard part is actually to showing that this is an isomorphism. Yeah. So, and this is what I will maybe just leave as a black box. Yeah. So, maybe I can still write this here. Propositions. So we're going to do Ayuk. This map here. It's an isomorphism. It's an isomorphism. So we will only care about the case when P is when for this P here, for P and S to S. So he actually does show it in greater generality, which is however not needed for us. He shows it for any smooth and projected map. Yeah. So so this is called ambidexterity for this term. So this is ambidexterity. It's called with this. Because it kind of identifies the left adjoint with almost the right adjoint up to this little list. So this is due to IU, and it's the proof is kind of, you see, it's kind of a simple statement, but it uses about 10 pages to figure it out. Yeah, so I still think there must be a better, quicker way, but I have tried to find one and have failed to find a better argument, and so that's why I think it would be too time consuming to write down these 10 pages now on the blackboard. But yeah, I hope it's okay for you to accept this as a given. So there is also other proofs of the same thing. So Scholze in his notes on motives has a proof in the case when n is 1 or p1. It's quite a clever argument, but it uses something that is not available in full generality in this kind of orientability here. And there's also another proof by Hoywa, but none of these proofs is really kind of, it's not easy. Yeah? Okay, anyway. Yes, please.
About the door space function. Yeah.
Yes.
Is there an easy way to say that, to see that it's representable by space, like a tensor by space?
Yeah, very good. Thank you for that question. That was what I wanted to also say, but forgot to say. So yeah, remark. The remark is the following. So Tom Fs applied to some F, let's say. Right, so F is a sheaf, a motivic sheaf here. So I claim this is Tom Fs of the model unit, tensor F. That's what I claim. Yeah? So, and why is that? So this is a bit of a little sorry, yeah, no, that I will only claim for F. So for simplicity, let me only explain it for F being an F such as A1S to S, and this little s would be the zero section, okay? It will be true in general for vector bundles, but not, well, probably also in that case after working a little bit more. But let me stick to this, yeah? Just to explain the structure. So what do I want to say? So F lower sharp. So maybe I write zero lower, zero for this section here, zero lower star 1, tensor M. That's what I'm looking at here. And so now I use the projection formula. In other words, linearities of this zero lower star here. So it's zero lower star of 1 tensor 0 upper star M. Okay. And then likewise, it's yeah, that I can do that, but I want to do something else first. Sorry, I want to first do it for the F. So let's do it for this one first. So the parentheses are like this. So it's going to be F lower star, F lower sharp of 0 lower star 1 tensor F upper star M. Okay. And now I use the projection formula for the other one. So 0 lower star of 1 tensor 0 upper star F upper star M. Okay, so this here is the identity, so I can forget about it, and then I get this. Yeah, this is the identity because it's a section, and so that's why. Yeah, so the upshot is the linearity of these two functors together with this being a section tells you this formula. Yes, in other words, this functor you understand as soon as you understand what this is, and this is this quotient. So it's not quite a scheme, but it's kind of a almost, yeah. And so this, what I last time we defined this SH to be such that this Tate sphere, which I defined as which has various definitions, but it can be the cofiber of GM sitting in A1. So that would be exactly this thing. Yeah. So remark. So this Tom space of, let's say, A1 S to S and the zero section, yeah, so exactly the situation here. This is what we called TS last time. Yeah, so in other words, rendering this tensor invertible is tantamount to saying these functors are equivalences. And so at least in this case, but that turns out to be true modularly for every vector one.
Sorry, there's a quick question. So I don't quite understand why we can think of this object as a space. So
You mean what I wrote here?
Yeah, so I mean, in general, this thing is it's an element of DES.
Yeah, right. So this is in quotation marks. Yeah. So it's you want to think of. I mean, this is really think of this as really being the X as a space over S. Yeah. I mean, this is how this is defined. Yeah. This is kind of in the context of SH. This was really the motive of X itself, but as a scheme over S.
Okay.
Yeah. So this was M of X, we called it, and this would be similarly the M of this open thing here. Okay. It's minus so. I mean, so far I didn't lie, and now, well, this is the co-fiber in that category, and I mean, there's no, I mean, this isn't, I mean, this is not a scheme in any sense, yeah, but if it was topology, then you could literally talk about the homogeneous co-fiber of that inclusion of spaces.
But so this for this to make sense, we need some like the factor D needs to be chosen so that it somehow is supposed to represent spaces, right? Like
it's just the co-fiber. I mean,
yeah, I understand what it is, but it's like if I take D to just be étale homology of like the étale derived category of étale sheaves.
Yes.
Like this wouldn't be necessarily a space, right? Or can I still try to?
What do you mean by a space in that context?
As in, yeah,
a representable pre-sheaf, you mean, like in this case?
Sure, or something that is kind of understandable in terms of representable pre-sheaves.
It would be the two-term complex of the representable pre-sheaf of the X and the one of that guy. Okay. That's what it is. It's not in its own right, generally speaking, the representable pre-sheaf of some other scheme, I think.
Sure.
I mean, this is in some sense the whole. Well, I should say maybe the whole point, but yeah, this is really just meant to be an intuition rather than saying there is some whatever honest geometric object that serves that purpose. Okay, good. So that's what I wanted to say about projective somehow based change, and now I want to use all this to kind of jazz it up and get to the powerful six-point formalism. So we have seen this in Bastian's talk beginning of the semester, so I want to be a little bit brief, but on the other hand, say what I should say, I think. So let's say this is now the category of spans or correspondences. Okay, so this is the tool that helps us to kind of squeeze all the data that we have so far into one box. So, yeah. And so let me briefly say it. So we fixed some category C. So this will be for us a certain category of schemes, and then we'll consider a wide subcategory that is stable under all kinds of operations, namely products and fullbacks along arbitrary maps. Yeah, so you will think of this as being a category of schemes, and this will be the maps that we have Schrieg pushed forward for. So we'll gradually extend this E as we go on. And then this category of spans, CE, is some infinite category that I'll just say formally. So the objects, once again, are the objects of C, and the morphisms. So on in this span category from, I don't know, X to Y is diagrams of form. You have this X, you have this Z here, and then you have Y. And this map, these horizontal maps, they're always supposed to be in this Y subcategory. So this is a morphism, and the composition is you take some such thing and you take another such thing. So let's say Z prime, Y prime, and you form the pullback, and this entire span is going to the composition. Yeah, so that's the idea. And in order to make this now into a rigorous thing, again, you have to be a little bit somehow well versed into writing this all up. But in principle, that's what. Yeah, so I think I'll just leave it on this formal level. So this is the category of spans, and now what are we trying to do? So here's the definition. So let me say a 6 functor formalism. What is it? It is a Lex symmetric monoidal functor from this category of spans. And so now we have to decide what kind of schemes do we want to allow. So we will massage this as we go on. But for the moment, let's just say we have all schemes. And the maps that we will initially sort of allow for this class here are the separated and finally presented maps. So this, you'll see why this comes up in a moment. So separated and finally presented maps. And so a functor from here to PRL stable. And so I will denote this functor by D upper star lower shriek or just D, depending on my level of energy. That's the notation. So some words I should say here. So Lex symmetric monoidal. First of all, these have to be monoidal categories for this to make sense. So what is the monoidal structure here? Well, this is easy. You just do kind of, you do it object-wise. Yeah? So if you have, for example, one such morphism and another one, then you do x times x prime and so on. Yeah. So that is one of what the monoidal structure is on this category of spans. And here we take the Lurie tensor product. Yeah? So Lurie tensor product, which I remind you, I don't know, did Pramod cover this in this course in Essen tensor products? Yes. Okay, then I may just say it orally. So you take two such presentable stable infinity categories, and their tensor product is the universal category such that functors out of there into something else are kind of component-wise Coulomb preserving functors out of the product. Yeah, that's the thing. The monoidal unit here would be spectra, and so this is kind of the natural home to work in. Okay, so let me. I think Bastian also kind of explained most, if not everything, what this buys you. Let me just kind of put a little spotlight on one or two of these properties. So I have to first of all say the notation. Where does this notation come from? So if you have a map in schemes, then you get two possible correspondences. Namely, one is you can regard it as a correspondence in this way, and if you do this, then you can apply D to it, and so we will call this F upper star. This is going to be D of this line. Okay, so this gives us the contrary functionality, so it will be this one. And similarly, the lower shriek, it's the other way around. Which is the D of if you do the other way around, you do x is equal to x, and then here you go to S. This is what we call F lower shriek. Yeah? And for this, the F has to be for the moment to be separated and finally presented. And we will see why this matters, as I said, in a moment. So that's the notation, and then maybe I will just say it orally because we have seen this. The functionality of this thing encodes base chain. Yeah? So you do, for example, which way around is it? No, you start here. Pull back along this map and then shriek push forward along this map. This would be one sort of composite, and the other one would be going this way. Yeah, and so that's sort of telling you the base change. Yeah, so that's extremely useful. And what's also useful is the Lex symmetric modality. So this tells us the following. So there is going to be the functor, which is called exterior product from D of x1, let's say, tensor D of x2 into D of x1 tensor x2. Okay, so this is really just the Lex symmetric monoidal structural map, if you want. Right? And Lex means this is not usually an equivalence. I mean, it might be, but we don't want to mess with that question. So I would really give a lot if I understood better what about this, but let's not talk about that. So anyway, we have a functor, and so this is the Lex modality on the level of objects, and then on the level of functors, this tells you that For example, if you have two maps, F1 and F2, let's say, then you can do such things as F1 times F2 upper star of something box something, and this is F1 upper star box F2 upper star, right? And similarly with the lower shrieks. Yeah. So again, this just is encoded in this one line here, in these two lines. Yeah, but these compute that this box product computes with upper stars and lower shrieks is part of the thing. Yeah. So in the notes here, I've written this out a little bit more in detail, but I think I can jump over this because it's been talked about sufficiently many times now. One other thing that I also want to say is the projection formula. Again, is encoded in this. So the projection formula, in other words, the linearity of F lower shriek is also encoded. Again, it's just formal nonsense applying sort of structures about an exponential functor. So the formula is F lower shriek of A times F upper star B is F lower shriek A and so B. Yeah? So once again, this means this is linear in the sense that well, you let the category at the bottom act by pulling back and then push forward, or just do that. Yeah, question.
So in the case of assessment, yeah, how far is the case from the natural initial point?
Yeah, it's a good question. So what we know is, I mean, if I write it out in such a way, it has no chance of being true in any sense. So what can be true, or what can be sort of contemplated is if you have a certain base scheme, and then you want to put the ads here. And so what is true is that, and this is really pretty general. So this comes out of, and I think I will mention this later in the course. Under reasonable assumptions on D, including, well, let's say not going beyond what we asked for so far. If S is a field, then this is a fully faithful functor. And I wish I had more to say. So what we think should be true is that the dualizable objects in here, if X and X1 and X2 are both proper and smooth, we expect this to be an equivalent. So D-dualizable tensor, I mean, if you put dualizables everywhere and X1 and X2 are smooth and proper, we think it should be true, but we don't have a proof. I mean, that works for motives. We do have a proof for entire cohomology, but not for motives. Unfortunately, this is one of the bottlenecks actually so far in the work with Timo.
When you pass into dualizable objects to this object, this is.
Yeah, well, this is just a cosmetical change. So when I said I do dualizable here, then in effect, this tensor product, if I do dualizable, then I actually would do int of it, and then if I want to, at the end of the day, pass to compact object again. So that's the definition of tensor product of these kind of small categories. Yeah. Okay, yeah, it's a good question. However, going beyond my skill set to really, unfortunately, answer. But yeah, this is. I mean, maybe I can say this is one of the main differences between these motivic contexts and things like quasi-coherent sheaves. So if D would be the derived category of quasi-coherent sheaves and X1 and X2 are, let's say, schemes, then this will be true. Yeah. So this is kind of a big difference between quasi-coherent sheaves and kind of topologically inspired motivic sheaves. Okay, so anyhow, a bit of a digression. So this is what we would like to have. Yeah, so that's the structure that we would like to see. And now the question is, of course, how do you get there? And this has been, on everyone's mind for, I don't know, some time. And I think nowadays, thanks to all these people working on this is now a very clear and nice picture. much nicer than it used to be. So let me say this. So I will use this work of Bastian Knossen and Lenz and Linskins, but let me directly say this is not necessary to use their particular work. There's other work by people like Liu and Zheng and Lucas Mann and Dowser and Kuiper. So there is a bunch of kind of approaches to the question, given such a 4-functor formalism, how do you jazz it up to a 6-functor formalism? Yeah. So, but what I like their work in some sense most, and so that's why I choose it here. But it's an expository choice in some sense. Anyhow, what's going on here? So, in order to state it in the best way possible, we have to slightly replace this here by something a little bit finer, and this is the so-called infinity two categories of spans. So what is this? So the notation is a bit long, but here is what it is. So C is again our category of schemes eventually. E will be these separated maps, and for these technical reasons finally presented. Okay, that's not crucial for the moment. T will be proper and finally presented maps, and I will be quasi-compact open embeddings. Okay, so this is what you should have in mind. And so now, of course, but this definition here works in large generality. And so let me try and say kind of informally what it is. So the objects are again the objects of C. And the morphisms are also like it used to be for the span. So morphisms, let's say one morphisms are the one morphisms of this span that I alluded to earlier, right? These zigzags. And so now this two here means this is a two category. And so the two morphisms are as follows. So if you have some, let's say X, Y, and then you have a map. So this would be this triangle here is a map from X to Y, right? And so I have to tell you, given some such morphism and another such morphism, B, what is how many two morphisms do we have? And so what they do is they say it's diagrammed like this, where this is a map in P, this is a map in I, and these, like before, these are maps in E. Yeah? So this is by definition the two morphisms from kind of this map to this map. Okay. Okay. So this is, and now of course again this is just a little bit wishy-washy here. You have to properly define this, but at the end that's what you get. Yeah. So they do this precisely by talking about Siegel spaces and so on. But I think we can live with that level of precision here on the blackboard. So that's the thing. And of course, you see, you can not allow any interesting two morphisms, and then you get back the original one. Yeah, so this is kind of an extension of that first approach, first concept. And so why do I bring it up? I bring it up because this thing has now a very clean universal property. And to state this, I have to make a definition. So we pick a functor from C to some D, where this D is also a two category. And so such a functor is called I T byte adjointable. If all these, so let's say P upper star, so this is my notation for f of P, like before, yeah. So the f here wants to be this 4-functor formalism. Now I call this D as well, but that would be the D from before. So anyway, the condition is that this P upper star has a right adjoint, which I denote P ortho like before, and this is true for any T in this class P. Yeah? So this will be for covariance in a moment, and then the other way around for the I. For all I and I, we have I upper star has the left adjoint, I lower sharp. Again, this is what we are used to, right? So this makes sense. And now there's a relation here. Plus for any Cartesian diagram, So xy, y prime, x prime. So we have p prime, I prime. That's a split Cartesian diagram here. We want a certain compatibility between these adjoints, namely we push forward along p and then we start pushing forward along I prime and then down using p. So it's I prime lower sharp. No, it's the other way around. Sorry. Yeah, I mean, I have to do that both anyway. So I lower sharp p prime lower star. There is a certain natural map from here to p lower star I prime lower star. So how do we get this map? Well, this is the length adjoint of I upper star, so you can put this on the other side. Okay. So imagine there was an I upper star here. Then you do a base change. Then you have a p prime lower star in front, and then the I prime upper star, and then you fool around and get a map. Yeah, so there's a natural map that's part of the existence of the adjoint, and this wants to be an isomorph. So for all Cartesian diagrams, this is an iso. Okay, that's the condition. This is what they call IP by adjoint group. And I mean, I should say, of course, such a condition has certainly been considered, by at the very least people like Deline and so on. But now this nice formalism here is in place. So let's take advantage of it. Now here comes their theorem. So this is the main theorem of Clausen, Lenz, and Limskins. So let's C be the category with finite products. Yeah, so like this. And if we consider I, P in E in C, so these are certain wide subcategories. Let these be such that so there is a bunch of conditions, which however are harmless in practice. So each morphism, let's say F in I intersect P is n-truncated for some n. Yeah, I remind you, n-truncated means you have this map F, and you apply, if you have a map, then you can do its own diagonal, right? So if you have x to y, then you can consider x goes to x times yx. So this is the diagonal of this. And n-truncated means you do this a number of times, and then eventually you'll get an isomorph. That's what n-truncated means. Okay. And then the other one, the next condition is I and P are stable under base change. And also there's a cancellation condition, left cancelable, they call it. So this means if G and F are, for example, in I, and G and F is in I, then also F is in I. No? Again, this is going to be harmless. I will comment on it in a moment. And then so far the E didn't show up. The condition is that all morphisms in this class E are of the form E is some P after some I, therefore E and P and I. Okay. So these are the technical assumptions. And now what is the conclusion in some sense? So that finally DB is symmetric monoidal BT2 category. So for us, we will only really care about PRL stable with not necessarily just its isomorphisms. So think of that. And so now the statement is then we can contemplate Lex symmetric monoidal functors from C up into D. Okay. So this is something which we will have, right? So the functor SH, for example, is such a beast. And then Then we have Lex symmetric monoidal functor out of this span category. C, E, P, I. My apologies for the notation, but once you have to write it down. So P, I, D. So we have, of course, this forgetful functor, right? We can C maps, or rather C op maps into this span category. This is a so-called, what they call locally faithful functor. So locally faithful means it induces faithful functors on all home categories, right? So notice these are all two categories, well, except for C maybe, but so these here we really allow non-invertible homomorphisms in these functor categories. So on the level of functor categories, it's faithful, and what's more, and that's the actual relevance here, is the point. The image is describable, so its image on objects consists of what? It consists exactly of these IP by adjointable less symmetric functors, and also at the level of morphisms. Yeah. So the upshot is, given an IP by adjointable functor in this sense, from C op to D, there is basically one way of jazzing it up to this span category. Yeah. And so this is, it's in this sense, it's stronger than what some of these other papers do. These other papers, they are doing things up to the effect of, given a functor with these conditions, they construct for you a certain functor out of the span category, and all of this is very kind of natural and so on, but sort of they don't have this precise universe property. Okay, so that's their main theorem, and now we can start using it. So we will basically apply this theorem and check that SH and other nice functors in here satisfy all these properties, and then we are happy. That's the next steps. And you see most of the walking work we have already basically done, right? So here's the theorem, which I want to again attribute to Ayub. So Ayub, of course, didn't use this language, but of course all the somehow, how to say it, the meat or the substance of all this is certainly should be credited to him. Then there is an extension of functionality he did, which initially was only for quasi-projective maps to all separated maps due to Zinsky and Eclipse, and then there's some epsilon in Timo's and my work that even gets rid of this separatedness. So here's the theorem. So let D, so I write maybe D upper star to remind us what the functionality was. So I'm looking now at QCQS schemes op to PRL stable. Okay, so let this be a 4-functor formula. In other words, a Lex symmetric there are 3 functor, I don't know. So 4-functor we call it. Okay, and then if D satisfies localization, then also A1 invariance. Then this TS should be tensor invertible. Or this Tom endofunctor should be an equivalence. And D is Zariski sheaf, a sheaf of categories for the Zariski topology here. Then D extends, I want to say canonically, to a 6-functor formalism. Yeah, so in other words, here we have schemes QC, QS op. Here we have the original functor to upper star to PRL stable. Here we have this category of spans or correspondences on QC, QS again. And here I will put these separated maps of finite implementation. And so there will be a functor, I will denote D upper star lower streak that extends this. Okay, that's the statement. And so notice all these assumptions here are, of course, verified, for example, for SH. So this will buy us the 6 functors for Motivic Sheaves. And yeah, how does this now work? I mean, so as I said, much of it we have already done, except for some fine print regarding basically these maps. Sorry. I said separated, but I don't actually want it. Let me erase it. So that's this epsilon that I referred to. So just finally present the maps. Okay, now I have to erase something. Only question is what? We do this. So the main thing on the board here is this map. So maybe I'll leave this one map here to erase the clutter. And so,
can I ask a question?
Yes, please.
The TS, suppose it is also like T1 point that.
Yes, yeah. So the TS was. So there's different ways of sort of talking about it. I defined it in the context of SH as the motive of P1 pointed at infinity, but maybe slightly more, how to say, organically. I mean, I explained how this is equivalent to the cofiber of the motive of GM mapping to the motive of A1. Okay, so this came from, you extend this A1 to A1 and so on, and this infinity to A1, etc. And so this is exactly what earlier I called this Tom space of A1 with a zero section, basically. Yeah. So maybe it would have been better if I had talked about that actually in that charlatan. But yeah. Yeah. Mm-hmm. Thanks for asking. So so you might want to rather say this Tom space object is invertible if you prefer. But okay. Good. So now, how does this work? So we will, of course, use that theorem, obviously. And so let's have a look at the assumptions. Condition 1. Sorry. First, I have to say it's 2 steps. So the first step is we want to apply their theorem to what? To E being, like I said, separated and finally presented. And I and P, it's already gone. I was these quasi-compact open embeddings, and P were proper finally presented. Okay, so this extra adjective finally presented and quasi-compact you might not be used to when you read about SH. So this is only necessary in these pro etal and pro named words. Yeah, so that's maybe not the main focus for the moment, but anyhow, let's say what's going on here now. So each such F is n-truncated. Well, this is trivial because the category that we work with is the category of schemes, which is just an ordinary good old category. So if you have any map, you do its diagonal, and you do the diagonal again, then it's an isomorphism. So these are all truncated. So that has nothing to do with that geometry. This is just true for any ordinary category for free. Then what about this? So these classes should be stable on the base change. Yes, check. And left cancelable, that's also true. Yeah, so this is kind of one of these standard properties of proper maps, for example. So that's also fine. And now what about this? So this deserves some ink or some chalk. So let's say about condition number 3. So there is a theorem, so-called Nagata's compactification theorem. Nagata tells us that this statement is correct up to a small modification, namely up to forgetting all these adjectives finally presented. So Nagata proved that let's say separated maps without finally presented are no wait, what do I want to say? Sorry, one second. So separated and sorry, here I have to be precise. The finite type maps are precisely the ones that you get by composing proper and finite type with quasi-compact covariant values. Okay? I mean, I hope this makes sense. Yeah, of course. So what I'm trying to say here is every such map can be written as a composition like there. And so the only difference between this classical statement and what we want here is this, that we have to make sure if this map is actually finitely presented, then one can find these also with these extra finiteness conditions. And yeah, I'm wondering, so it's in the notes. Maybe in the interest of time, I'll just briefly say it. So here's some Noetherian approximation going in. So very briefly, the thing is the following. So you can say this category of QCQS schemes is the pro category of finite type schemes over Z, and pro category with affine transition maps. Yeah, so what I'm saying here is if you have xi, xj, so such a pro system, and these maps are affine, and these are all of finite type over Z, then this limit, so here this sends such a system to the limit of these schemes. This first of all exists as a scheme. Second of all, it's quasi-compact and quasi-separated. And what's more is that every such QCQS scheme can be presented in such a way. And then finally, that these finite type schemes are kind of co-compact, if you wish. Yeah? So homing into them preserves co-filtered limits, I guess. Yeah. All this is so-called Noetherian approximation. And this is the standard tool to jazz up things you know about maps between finite type schemes to general maps between QCQS schemes. Yeah? So what then you have to say is, given such a separated and finitely presented map in here, it will come from a finite type map between schemes of this form, which is separated and finally presented again. And then in here, since everything is Noetherian, these two things don't make a difference. That's kind of the thing that's going on. So it's a little bit technical, but somehow maybe not the main thing here. Yeah. So, oops. In other words, Nagata plus this Noetherian approximation tells you this condition 3 is satisfied. And now I can erase this because now we have checked it. I've learned something from Michael yesterday. That's erasing things after they have been addressed. So that was a very smart move. Okay, so that is what we checked, and what still has to be said is this IP by jointable condition. And so this is in fact also easy. So remember our assumptions were here, localization, blah blah blah, all these, and then we have to still use that. Yeah. So far we've just kind of checked the conditions that have nothing to do with the D, but under our assumptions, we have in fact proved, well, up to this one thing about Pn, that so under our assumptions we have seen the following. If you have x prime to x, and here you have u, so let's say j, p, and u prime. If you have such a Cartesian square here, then I claim that j sharp p prime O star is in fact isomorphic to the other way around. Yeah. Why? Well, now we use all the thing from before. So it will be equivalent to seeing that this is true after j upper star and I upper star, where the I is kind of the complement. Okay. Yeah. So we know under localization tells us these two things are jointly conservative. So let's do that. So we apply J upper star to both terms. Well, this will cancel the J lower sharp here. And here we can do base change because we have it, yeah. So we use base change for the P low star to swap it around. And so then again we use the full faithfulness of the lower sharp. Yeah. So this is the easier part. And this is also fine. So let's look at this. So we do I upper star. So here we get 0, again by localization. What about here? Well, here we have I upper star, P lower star, J sharp lower, J prime lower sharp. So now using base change, so and it's here where we use all the glory of this, yeah. So using base change, we have, if you wish, maybe you can call it P double prime lower star, I prime double star, A prime lower sharp, where the P double prime is the pullback here. So this is no longer relevant, but here again we have 0 by localization. Okay. So in other words, localization and proper base change, I mean, as we know, comes from all these assumptions, tells us this biojointability. Yeah, that's it. So that's the proof of this here. Well, half of it, maybe the first step, when E is separated and of final presentation. And the next step is to overcome this separatedness. Yeah. So what we have so far, maybe let me pause for a moment and kind of mini summary so far. For a separated map, E, I call it, we have that E lower sharp, E lower shriek is P lower star, J lower sharp for this factorization. Yeah? So this comes out of how their theorem works. Yeah? So that's what we have. So for separated maps, we know what to do, and that's what we want to do as well. Yeah? So that's where we are. And so the extra step now would be to overcome this condition of being separated, which can be overcome using descent. The only question is, do I want to talk about that or not? Maybe not. Let me just briefly say the idea. The idea is the following.
Sorry, can I ask a question?
Yes, yes, please.
In this the functor categories are infinity 2 categories.
Yes.
So that means, for instance, if you have two 6-functor probabilities, D and D prime, you can morph it from D to D prime. Some sort of realization functor.
Yes.
So does it suffice?
Well, that's not that.
Sorry.
Yeah, no, it's okay.
So, and you want
to
have on every X, and you want to create that sort of realization on span.
Yes. Then you will look at what I have kind of very quickly said here. So this is going to be a morphism, right?
Yeah.
And you need to check this morphism is again IP biojointable, which means that we already know that sort of here, this kind of formula holds for both D of blah 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 and D prime of blah blah blah, and you want this what you polarization this functor to commute with the P lower star and the J lower sharp.
Yeah.
And then it will.
So you get
it will extend. Okay. So I wanted to very quickly say the idea of the definition of this extension to non-separated maps. So if you have a non-separated map X to Y, and you would like to say what on earth is F or shriek, well, you will say this. So you can say I cover my U by my Y by U's, and here or maybe by V's. And so let's say I cover these by affines, and I will be able to cover it in such a way that sort of they map to each other. So I already know what G or shriek means, yeah, because if these are affine, that's in particular separated, and then there is a Zariski descent argument telling you there is exactly one way to defining this in a way that gives you that after pulling back along all these open embeddings. Yeah, so that's That's the idea. And here in the note, I've included some discussion about it. But maybe that's not the main thing. So what I think is important to know is that, and this is I think really we should credit all these people who work on the six-func formalism. It's now kind of the perspective has changed a little bit in the sense that we have these few kind of abstract conditions, and then it just falls out. Yeah? So which is kind of different than how Ayub initially set it up. I mean, the end result is the same, but the road is a bit shorter. Well, shorter at the expense of citing all this abstract work. But yeah, okay. Anyway, that's the status. And so what I want to talk about now is this so-called category of kernels, which is again a recent advance. So what is this about? So we now have these base change functors, lower shriek commutes with upper star and so on. Yeah? So this is beautiful. But whenever you come across such a situation where you have, let's say, some f which is not proper, and you want to say, hey, is it true that I can compute j upper star past f lower star? It's not clear. I mean, the machine doesn't. It just stays silent. And so it's an important question to figure out, given a sheaf f in d of x, right? So let's say this Motivic sheaf lives here. You push down, pull back, or you do it the other way around. So you do have that map, and you might want to ask, hey, for my favorite sheaf, is this maybe an isomorphism or not? Yeah. So that's one of the benefits of this categories of kernels that I'm going to talk about now. So. Here it is.
The question here is that for general, like we know it for, say, proper.
Yeah, so what we know now is that if this map little f is proper, it's fine.
Or open.
Or if for the moment we know if J is open, and we could also extend this to J being a smooth map. I'll comment on this later. So let's say if you have certain conditions on the map G and or F, you know this for any sheaf capital F. However, let's say F is not proper and G is not smooth. So certainly a situation that you might be interested in. Then, in general, this will not be a functorial isomorphism, generally speaking. Yeah. However, it can happen that for certain sheaves F, it actually is an isomorphism. That's what I'm saying. Yeah? And so in some sense, we are asking what unusual base change things will you have? Yeah, that's kind of the spirit. Going beyond proper base change and smooth base change. So, and this is what this category of kernels somehow organized nicely. I mean, among other things, it's not just about this, but that's part of the appeal. Yeah, what is it? So I need to fix some notation, or I want to fix some notation. So I want to fix some category of schemes here. So that is supposed to have finite limits, and so including the final object. And so I want to write span C for span of this C comma all. So in other words, I want to, just for the simplicity of the discussion, I want to focus on the case when we have shriek push forward for all maps actually. And so if you look back here, we had it not quite for all. So in practice, what this means is we can say, let's say S is a QCQS base scheme. Yeah, so maybe your favorite ground field or something like that. And this C could be finally presented schemes over S. Yeah. If for this choice we would know that all, and then we would put the C here instead of this, and then we would have, then this would not be an extrapolation, yeah, because all maps would automatically be finally presented.
Sorry, so this thing is what from what I remember from also what Lucas Mann does, where he assumes that everything is shapeable.
Yeah.
But then, I mean, his work, for example, on like representation theory from this six functor probability perspective, not everything is shapeable. And also, like in many action cases where he works for instance, stuff, not everything is shapeable. So is this something that can work? Is this for the convenience? Is my question.
To a certain extent, yes. I mean, let me write something down, and then I'll say sort of where you have to start being careful. I mean, it's basically, it's kind of whenever you write down a shriek, then you have to know what it means in some sense. Yeah. And so I'm trying to sweep this under the rug by making this restriction, but yeah, this you can certainly massage this. Yeah. So okay. Anyway, this is my notation. So think about this here, and then so that's the notation that I will use, and then again I will use this notation D or D star trig for our six functors for the URL state. Yeah. So that's the notation. Okay. And now what is this category of kernels? Definition. This category of kernels, so I write ker or ker D, is the following. It's again an infinity 2 category. This the infinity category given as follows. So the objects are just the objects of C. So in other words, nice enough games. Okay. The morphisms form in this category of kernels between two such schemes is what? So this is supposed to be now a category, right? An infinity category. So this is going to be D of X times Y. That's the definition. So a morphism is a sheaf on the product. Sounds crazy, but that's what it is. And what is the identity? The identity of some X. So this has to be a sheaf on X times X. And so this will be delta lower shriek of the monodal unit. And so it's here already where you have to at least start being careful, because you know if your X is, let's say in our context, if the X would fail to be finally presented, then the diagonal, and also not separated, then the diagonal is not clear exactly what the delta shriek means. I mean, I'm not saying this cannot work at all, but at least this symbol you have to somehow mean to it. Yeah. Anyway, that's the identity. And the composition. What is the composition? So if I have a map from X to from Y to X, then maybe let me write it this way. So this is a morphism. So in other words, what is that? This is really nothing but a sheaf on X times Y. And another morphism from Z to Y, which I call N. So this would be a sheaf on Y times Z. Well, then the composite is going to be a certain sheaf on X times Z, and you can guess, I guess you only have to guess once what it is. So let me write it down. So M composed with N is the kind of the expected expression. So you do a shriek push forward like that, and you do a pullback with M, and tensor this with a pullback from with what pullback? Sorry, I wish. Yeah, it was the first start of that. Yeah, so the notation here is you have X, Y, Z, X, Y, Z, and then you have the usual pair of pens, quote unquote, diagram with all these projections. Yeah, so here lives your m, which lives over here. Your n lives over here. You tensor them up together, pull it back along. Pull it back over here, and then push it down. That's going to be g1x times z, and that's declared to be the composition. Okay. Now, of course, again, this is not a serious definition. Again, you have to be more careful about what that exactly means, because how is this composition associative, etc. So this problem has been solved by maybe I should mention the reference. So as you already alluded to, so what I'm lecturing about here shows up in the work of Claudius Heyer and Lukas Mann. It's also going back, it goes back to work, I think Lu and Zheng would be probably the initiators of this kind of thought here, and to see that this is a meaningful thing to do. Yeah. So Heyer and Mann, they give a rigorous exposition of what this means. So maybe I want to include that because, or at least allude to it, let's say, because this is going to be important. So how does this work slightly more precisely? So the insight here is the following, and that's an interesting insight in its own right. So let's say, a remark. A remark helping to make this into a rigorous definition. This category of spans is enriched over itself. Why? Well, first of all, it's so that every object here is self-dual. Any object X in here is self-dual. So this, I think you will have seen this, yeah. So you have this span here would be the co-evaluation, and the other way around. You have the evaluation, and then you check the definition of dualizable objects works out as expected. So every object is self-dual, and in particular, this category has internal Homs, so the internal Hom from X to Y is just X times Y, yeah, because it would be X dual tensor Y somehow, but that's what we get because of this self-duality. So in other words, you see that this, somehow this internal Hom gives you this enrichment over itself, and this can be then used to do the following. So one has this category of spans, which is a span enriched category, and then from here we have this Lex symmetrical model functor, BRL stable, and there's a general sort of nonsense taking this category with its enrichment over itself, and then you use this Lex symmetrical model functor to get a category with a different enrichment, and that is sort of this one. Yeah, so that's kind of roughly what's going on. So you have this category is enriched over itself. Okay, so the Homs anima, if you wish, are not just anima, but rather this category itself. Yeah, and so then you have this Lex symmetrical model functor. And then what I'm saying is, the general paradigm would be you have some category, let's say M, which is enriched over, let's say, A, and you have a Lex symmetrical model functor from A to B, Lex tensor functor. Then you can cook up a new category that has the same objects as before, but the enriched mapping space is between two objects is what you get when you apply this function. Yeah? And that gives you exactly this kind of thing. Yeah? Because you see, this is kind of, if you wish, D of the internal Hom from X to Y. So, okay. What I'm trying to say here is there is a nice little input here, this self-duality, and then a little bit of abstract nonsense in order to make this into a well-defined definition.
Yes. Maybe simultaneous, but by dynamic reconstruction, that usually that this dx times y will also correspond to column preserving functions in parallel from dx to d1.
No, not unless you know that d of x tensor d of y is equal to d of x times y. So what you were saying is d of x times y would be question mark fun L of d of x to d of y, right? That's what you were saying. And so this would be, so if there's justice in the world, this is dualizable. So this would be, and maybe even self-dual, again, using this kind of thing here. So in good cases, this would be d of x tensor d of y. I mean, that will be true in good, I mean, sort of appropriately formulated. But this is the box product functor, which again will not be an equivalent necessarily.
I thought it was true for.
This is true for not few code, but not code. It's
in my story.
Yeah, no, it's a good question. I mean, in some sense, this is telling you that this category of kernels here. Yeah, I mean, thanks for asking. So I think I want to. Yeah, how can I say it? I mean, yeah, I don't know. I mean, it's so yeah. So okay, yeah, that's what it is. But yeah, your question brings me to a good point. And of course, you might wonder, okay, hey, what are some morphisms in there that we should care about? And so this can be nicely subsumed into the following lemma, which again is showing up in this paper of Higher and Bunn. So I'm almost taking everything from them right now. So we have this original category C, and we have C op. And then we have this span category, right? So these functors are, I mean, all these functors are kind of the identity on objects, and on morphisms, this would be this upper star kind of thing. And here it would be here it would be the upper star kind of thing, and here the lower shriek type correspondence. So, okay, that is so far so good. Then we have a functor to this category of kernels, which I will explain. And then we have another functor to PRL stable, and this one here would be the composite. So what are all these beasts? And before I say this, I want to say all functors, except in general, psi are actually symmetric modular and not lex. Yeah. So, and now I should say what are these functors? And so this gives you kind of an idea. Okay, there is going to be a certain supply of interesting morphisms. So psi is the identity on objects. Yeah, so when you hear the object for just schemes, basically here the objects are also schemes, so we don't do anything on the objects. And what do we do on the morphisms? So psi sends a morphism, which is the correspondence. So z, what's my notation here? Now I call it y. Z x. So this is the morphism in here. I have to give you a certain sheaf on y times x. What is it? It's you take z mapping to y times x, right? You have these two maps, you can map the product, and do lower shriek of the modular unit. So this is an object in d of x, or maybe I write y times x, which we declare to be the morphism in D. Yeah? So in other words, the correspondence gives you a certain natural kernel, you might say. That's one thing. And the other thing is, what about this second thing?
Sorry, can I ask something?
Yes, please.
Maybe it's stupid, but it's just for me, it's one of the hardest parts in research for using. I mean, isn't there a specific reason why when we construct stuff like that, we use now we take the low shape of the unit. Okay, why do we do something like the push forward? It's like the pullback of some other pullback of the push forward. I mean, why is this? Why should they?
Why is this natural or?
Yes, yeah. And not only this, in several arguments, this is the case.
Well, what else would you like to take? I mean, you mean the star push forward?
Yeah, but then it would be okay.
Yeah, okay, it's a good question. If we put the star push forward, it's at least an object in there, but then you will run into problems when you do compositions, right? So you see, if you do tuck tuck and another correspondence like this, you of course want them to be compatible, right? And so you see, if you imagine some other correspondence, then you will involve at the end of the day a certain upper star function.
Yes.
And then this wouldn't work. Yeah, so that's why. So I mean, that's as far as I can see the only way of making this functorial. Yeah.
Okay, so for example, when I try to find something, it's looking at the compatibilities is what is going to mostly dictate the kind of choice of function or beautiful.
Yeah, totally. I think there's almost no other way of doing all this. I mean, in some sense, you see, yeah, I think there is no other way to do it.
Yes, it's also possible because lower shriek is the functor encoded.
Right. In some sense, if you believe in this being the composite, which I have yet mentioned, then it has to be that. But of course, I mean, you could. I mean, for example, you might dream about taking the Verdier dual of this guy. I mean, and so on. Yeah. So I'm not saying that this is the absolute only way of doing some such functor, but at least that's the one that jumps into your face. And yeah. Okay. That is the first functor. What is the other functor? Psi. So once again, it goes from this kernel category to PRL. So on the level of objects, this is just going to be D. Yeah. And on the level of morphisms, now we have to do what? So given the morphism, so if we have M, which is the morphism in this kernel category from X to Y, right, which once again is D of X times Y, then I have to now come up with a functor from D of X to D of Y. Or rather, here I have, is it the typo in the notes? Let me see. I think this is the typo in the notes here. So I'm looking at the following functor. So it's pi y Lord Greek pi x upper star blank tensor f. And again, this is a formula that you will recognize if you have ever looked into what a Fourier-Mukai transform is or so. So this is really coming up over and over again. And there you might be, I mean, in response to your question, so there you look at lower star functors rather than lower shriek because there is no lower shriek in the first place. And the lower star functors in the context of coherent sheaves, they do commute with fullbacks. Yeah, so that's, but this is not, I mean, this is just a reflection of a change of notation and in some sense the same thing. Yeah. So, okay, that's the functor here. So which goes, like I said, from D of X to D of Y. Yeah. And so now, of course, you can fool around. For example, you can look at this composition. So if you have some such correspondence, like here, this is now your kernel, and then you plug it into this thing. What I'm telling you is this is going to give the, so if I have a name, let's say for this here, so then we can observe the following. So psi of phi of this correspondence here, Z, Y, X, G, F. So, well, it's whatever this is, and then you do this, and then you're going to get, lo and behold, F Lord Greek, the other side. Yeah? So in other words, this is indeed the composite. Okay. So all this follows from unwinding definitions. Okay. So far it's just a crazy definition, and you might not buy its worth yet. The time is up now, so I think I will stop here. What I will do next is I will introduce this notion of suave and prim objects and maps. So this is again a very, in my opinion, really a striking shift of perspectives, similar to this notion of descendability, right? So the spirit is a little bit, we have certain conditions in algebraic geometry, so like smooth and proper maps and so on, but it turns out to be just working just as well, basically expressing all these conditions in terms of this category of kernels here, and that's what we will do. Yeah? So we will kind of define these notions and play around with them a little bit and see how this relates to Verdier duality and so on, and this is all going to be a very nice kind of game, if you wish, of doing algebra in this game. Yeah. Okay. Cool.